Okay, welcome to this second lecture. So, as I announced last time, the first purpose of the lecture today is to provide some motivation, some illustrations of the kind of thing that I did last time, which was basically computing the variance of additive functionals of Markov processes, reversible Markov processes, diffusion processes. And also I want to provide some motivation for what is to come later. What I'm going to do now, in the beginning of this lecture, is discuss a little bit of one model from physics where well, not exactly a diffusion in a random environment, but something a little bit like it pops out. And okay, so I think it's interesting to have a look at the way physicists view the kind of objects that we manipulate. So the model I'm going to discuss, briefly discuss actually, is a model for electronic conduction, which is due to Mott. It was introduced in a paper in '69, and it's called Mott's variable range hopping model. So why I use this is because actually my first idea is because this is, so to speak, a true model from physics with a strong physical basis. And now, it seems that this model is becoming fashionable within probabilities also, due to recent works. Yesterday, David Croydon and Professor Kumagai were discussing some features of this model. Okay, so I'm not going to go deeply into the physics of this model because I would be unable to do that. So what I want is just to stress a couple of features of Mott's model that will be some kind of motivation for the point of view that I want to use for diffusions in a random environment. I should say that my advisor in physics and collaborator, who gave me a number of quite valuable advices about what to say and what not to say about Mott, is Professor Alessandra Fagionato, who is certainly one of the best experts in mathematical physics about this model and other models, indeed. So, just to introduce the model, this is a model for electronic conduction in doped semiconductors. So, you have a semiconductor, and these semiconductors contain low density of impurities. So this is my semiconductor on the blackboard, and there are impurities which are scattered around in a certain way. These impurities associated to each location where you have an impurity, there will be a certain energy mark, an energy level, E of x for this point x. Okay. Then there are electrons in this material. So due to some localization effect, the electrons are only allowed to be at the impurities. The wave function is concentrated on some of these impurities. So we have localized electrons. And what happens is that in the absence of any force, the electrons will be in one of these points, but they can change, they can move. They can jump from one point to another one. They can hop from one point to another one. So you have a hopping dynamics. Now, how does it do that? You should describe the rate at which an electron can hop from one impurity to another one. And this is, so that depends on the point, let's say the electron starts from, and then it's going to jump to another one, so from some point xi to another point xj, with a certain rate. And the rate depends on two things. On the one hand, it depends on the distance between these 2 points. So the rate is some function of the distance. And it also depends on these energy marks which are attached to the two different locations. So it depends on the energy of xi and the energy of xj. And so depending whether the energy of the target location is higher or lower than the energy of the starting location, then you need some energy or you lose some energy. And that is related to the fact that there is a phonon which is being absorbed or ejected. Anyway, the important fact for us is that these rates are symmetric. So they depend on the distance, which is symmetric, but also on the energy marks in a symmetric way. So these weights are symmetric. So given the data, and the data are the localizations of the impurities and the energy marks, then you have a random walk, a reversible random walk. And now one has to specify how the impurities are distributed and also how the energy marks are chosen. So it's a common thing in the case of a disordered environment to use a random environment with, which is statistically homogeneous. So we take for granted that the locations of the impurities, but also the energy marks, are random and they are chosen in a stationary way. Actually, the canonical choice is to choose for the xi Poisson point process. So you could assume that the xi form a Poisson point process and that the energy marks are IID with a certain law. If you do this kind of choice, then you definitely have a random environment, which is stationary. As a matter of fact, you have more than that because each impurity somehow creates small potential around it. And such an environment will be close to having a finite range of correlation. In particular, the Poisson point process itself doesn't have any long-range correlation. But if you choose the energy marks in an IID way, then you can think of this environment as being an environment with finite range of correlation, which will be one assumption that I will use later in the course. So with this choice, we should say maybe we have a finite range of correlations. Anyway. Now, this is a description of the dynamics. Well, it's not complete because I should tell you how one chooses the law of the energy marks, which I'm not going to do. And anyway, Alessandra told me she would need a whole seminar to explain to me how the law of the energy marks is chosen. And so, anyway, I don't really know why the physicists have a specific choice of this law. But that's not very relevant to the talk today. What I want to emphasize is the following thing. Now, what is the important quantity we should look at in such a semiconductor? So this is what people call the electronic conductivity. So there is some conductivity. So the first thing you want to measure is the conductivity. Now, what is the conductivity and how do you actually measure it? So let's call it sigma. So in physical terms, the conductivity is defined in the following way. You take your system, impose a small electric field in some given direction with a given strength, and that creates a current of electrons flowing in that direction, and this is what you measure. So we turn on electric force, constant one. So to be coherent with my notation, I will denote it by lambda E1, where E1 is the direction and lambda is the strength. And once we have this external electric field, then we get a certain flux of electrons in direction E1, J, which depends on lambda, also on E1, where I don't indicate it. And you measure that electric current in direction E1. And you define the conductivity as being the current induced by an external field, a small one, when lambda is small, and which you normalize by lambda. And lambda is small, that means, so mathematically speaking, this means that you send lambda to 0. So it's a derivative. It's a derivative of a certain quantity. Now, so this is the main physically significant quantity. Now, the problem is that one wants to say something about this quantity, to estimate it, or maybe compute it, but computing it will be too difficult. And it's not at all easy to handle this kind of expression. So if that was the only thing that we knew, then we would be a little bit stuck. But very fortunately, there is some magic formula, which is Kubo's formula, which tells you that you can express sigma as the diffusivity sigma, big sigma, in direction E1. So this is the expression that you can get from Kubo. And here, this big sigma is the same as last time. This is the effective diffusivity, or variance. This is the variance. And this is the diffusivity when you don't have any lambda. So this is at lambda equals 0, if you want. And this is very good news because sigma is something that is much easier to analyze. The big sigma is much easier to analyze than the small sigma for many reasons. So first of all, this big sigma is defined directly at lambda equals 0. So you can ignore the external field. You just look at the symmetric case. There are variational formulas for sigma, and it has this expression as a variance, etc., etc. So there are many estimates, and there are many ways to sometimes compute, but usually estimate this big sigma, which are much more effective than what we could do if we only had this expression. Okay. So that is first thing to be said. In the case of this model, let me make two more remarks now at this point. You see, it's a little bit. I mean, last time I spent the whole lecture computing the variance of additive functions of Markov processes, and nobody complained. So maybe because this is some problem that mathematicians consider as a nice and natural problem. But you see, from this discussion, that as far as I understand, in the physicist's point of view, it's a little bit twisted with respect to our point of view. There is what is the important physical quantity is not this big sigma, it is a small one. And it's only because of Kubo's relation, which makes a connection with the effective diffusivity, that physicists care about effective diffusivities. So, I mean, a priori, the effective diffusivity will not be considered by physicists as a physical quantity. It turns out to be an important physical quantity just because of this Kubo's relation. So the truth is that this is not an exception. I mean, Mott's model is not an exception. There is a similar discussion about the variance, the physical interpretation of the variance of a Brownian motion in the papers of Einstein, which introduced Brownian motion to us. And the discussion is more or less the same. That is, the variance appears because it controls the effect of adding a constant force to the movement of the minute particles in suspension in some liquid. So I think this is a rule that, from a physical point of view, the effective diffusivity often is only interesting because behind it there is a Kubo relation. Maybe before I go back to diffusions, just for your general culture about this model. So Mott's variable range hopping model is more specific because there are assumptions on the law of the energy marks. Now, one reason why it's interesting is because actually based on this kind of formula, you can estimate sigma. So for this specific choice of the law of the energy marks, which I don't specify, and it turns out this model shows very unusual and specific features when you look at it at low temperature. So in the rates there, so temperature is involved, and so one strong motivation for looking at this model is because it displays interesting features when the temperature goes to 0. So there are quite many references on the model in physics, starting with Mott's paper. So the origin of the model is quantum physics. If you want a description of the model in terms of quantum physics, you may look at papers or surveys by Bldg. And if you are more interested in the probabilistic aspects, then I will refer you to the many papers Alessandra and co-authors wrote on that model. I'm one of the co-authors, but there are many. However, even if we know things by now about the way sigma depends on the temperature, and also there are results about proving the invariance principle in this context, which are due to Alessandra with Pietro Caputo, etc. A full derivation of Kubo's formula is still missing. So in a very recent preprint, Fagionato with Nina Gantert and Michele Salvi proved this relation in the 1D case. But it's an open question to prove that. So the proof of this relation is still missing when the dimension is larger or equal than 2, for instance 3. Okay, so in the rest of the course, we will not consider this model. We will consider diffusions in a random environment like last time, and then we will see that we can prove something like this in the case we have a finite range of correlation. But in that specific model, because of the long range hopping dynamics, the proof is not done yet. Okay. Now, so one more remark. I said the conductivity is an interesting physical quantity. Now, when we measure the conductivity, so we have to measure the electric current induced by the force lambda, and this G of lambda should be measured in a steady state. So G of lambda is the current of electrons flowing in that direction, and at equilibrium. Or, let's say, in a steady state. Now, I want to discuss this a little bit more, in more details. Now, because what does it mean to measure this current at equilibrium? What is at equilibrium? So, physically speaking, it's easy. I mean, it's easy. You wait for a long time. You wait for a long time until things become steady. But we should be a little bit more precise about what we mean by steady state or equilibrium. So, what is at equilibrium? Well, we actually know it from the first lecture. What is at equilibrium is the environment seen from the particle. So we take the point of view of the particle. Okay. Let me be a little bit more organized. Now I want to define what a steady state should be in the, let's say, in that context or in the context of diffusions in a random environment, but the discussion is the same. And the discussion will be a little bit long. There will be two definitions of steady state. And now I'm heading towards the first definition. So, the first thing is we take the point of view of the particle. So you take the point of view of the particle. And a steady state is an invariant measure for that process. So with the point of view of the particle, steady state means, it doesn't quite mean, but a steady state will be an invariant probability measure. invariant probability measure. Now, think of that question in the case of diffusions. So if I go back to diffusions in a random environment. So recall that I considered reversible and non-reversible diffusions in a random environment. So I had these processes, x omega, say with starting point x of t, which is the Markov process, which is reversible, with a generator, which depends on small omega. So small omega is the environment. And the generator of this guy is a symmetric operator. It's 1/2 div A omega grad. Okay, so this is the one corresponding to the absence of external force. And I also had this x lambda omega now, as here, which is the one that we obtain by putting a constant force in the direction E1, and the generator of this process is 1/2. It has the form of this form, exponential v div exponential minus v a omega grad, where so v is the force that we apply. So v of x is just, I think, minus twice x dot E1. So I forgot the lambda. I should put the lambda somewhere. Maybe we can put it here. Okay. And when you have such a generator and you construct this one, then it actually corresponds to a constant force. If we were in the case of Riemannian geometry, then we would say that this is a conformal change of the metric. I mean, my claim is that what corresponds to constant force is exactly, it has to have this form. I emphasize this point because this is going to be important in the next lecture. Anyway, so we had these two diffusions, and then we defined the processes of the environments in from the particles. So we had this process omega of t, which is just you start the diffusion from the origin in the environment omega at time t, and then you shift the environment omega by the position of the diffusion. So this dot is a translation of environment omega by this position, and then we can also define the process of the environment corresponding to the lambda, which will be omega lambda of t, which by definition is the same thing, except that now we run the dynamics with the external field and use it to shift the environment. Okay. So when looking for a steady state, we are looking for invariant measures of the process omega lambda. Then there are questions about the existence of an invariant probability measure for this process. So this is a process that lives in a rather big space, in the space of environments. So you can ask about the existence of invariant measures, and you can ask about the uniqueness. So the questions would be existence and uniqueness of invariant measures. For omega lambda. Now, none of these questions is completely obvious, but the true problem is not really the existence, it's more the uniqueness. So in the next lectures, we will see that there are invariant measures for omega lambda, but the difficulty comes from the point that there are many of them. So we will see that we can construct invariant measures for omega lambda, and we can construct a whole family of them by considering laws of the environment with a finite range of correlation. So we will construct one invariance measure for each choice of Q. So Q was the law of the environment, at least for these Qs with finite range of correlation. And this is not the whole family. So the first thing we should do is select among all the invariant measures of omega lambda the one which we will call the steady state. And the way we do that is by saying that what we want to measure, let's say in that picture, for instance, what we want to do, I mean, if you were to measure the current for good, in reality, what you would do is you would start with some sample of the environment, then you would turn the electric field on, and then you would wait for some time, and then you would measure the current of electrons. So you would actually start with typical realization of the environment, which is sampled according to Q. And that leads to the following definition, that so we should call steady state for a given value of lambda. So we'll call nu lambda, which is a probability measure on omega, is the steady state if you have a law of large numbers. So if I use the same notation as before, it's, well, okay, let me write everything. So we have a law of large numbers. 1 over t is the integral from 0 to t f of omega lambda of s ds. This converges to u lambda of f, and we want this convergence to hold Q almost surely. So the important thing is Q almost surely. I mean, everything is important, but in particular, it's important that we ask for the law of large numbers to hold under Q. And this for a certain class of functions, but when we deal with the construction of probability measure on some space, then it's quite natural to ask this to hold for functions f which are bounded and say continuous. So, okay. So this is a definition of a steady state. This is definition 1. I said there would be 2, so this is the first one. Okay, then if you have such a thing, then u lambda is indeed an invariance measure for the process omega lambda. And also, there can be at most one invariance measure that satisfies this law of large numbers. So we have a well-posed definition. And the steady state, if it exists, will always be unique. By the way, this definition absolutely mimics the definition of what Sinai-Ruel-Bowen state is in dynamical system. So it's completely analogous to SRB measures in dynamical systems. Now, maybe just before I erase the other blackboard on what. So we should keep in mind that what we would like to do is to compute what corresponds to the conductivity. So what corresponds to the conductivity, so the current of particles in that model with diffusions will be the effective drift, which I call L. So our aim will be to look at the effective drift of the diffusion with lambda. So we should prove that this limit exists, but if we have a steady state, then it will follow from that. And then eventually we want to compute its derivative. So we should also prove that the limit when lambda tends to 0 of 1 over lambda L of lambda exists. And to justify Kubo's relation, then what we expect is to find sigma E1. Okay? So this is what we want to do. And we don't quite know how to do it in full generality, but okay. In the context of a diffusion process, this derivative, if it exists, rather than calling it conductivity, it's usually called mobility. Okay. So that would be the program, if you want. Okay. So, what can we say? So this is the position of the problem for diffusions in an environment. You can ask this kind of questions in a quite general setup. There is a formulation of these things in a general setup. So I'm not going to be 100% precise about that, but you see, what we start from is a reversible dynamics. So in the case of diffusions, the reversible dynamics is the dynamics of the environment seen from the particle. So you can imagine doing something like this in the following sense. You start with a reversible and ergodic Markov process. So certainly you have to assume a little bit of smoothness, but okay, I'm going to be quite loose. And then you consider a small perturbation. So that Markov process will have an invariant probability measure, an invariant and ergodic probability measure, which I still denote by Q. And then you will consider a small perturbation with some parameter lambda. And you ask about steady states. So you can take the same definition as there. And you ask about the existence and uniqueness of the steady state and the derivative. So ask about existence, uniqueness, well, uniqueness is not an issue, but existence of the steady state to lambda, and also whether you can take the derivative. So the derivative of Q lambda at lambda equals U. So there are assumptions under which this problem can be successfully attacked. And one first result is that we can solve these questions in the case where you have a positive spectral gap. So positive spectral gap for the dynamics you start from. So if the unperturbed dynamics has a positive spectral gap. Now here what I mean by positive spectral gap is a spectral gap, the usual thing in L2, in L2 of Q. Then there is a steady state, and you can take the derivative at lambda equals 0, and these are results which are proved in papers, in a paper by Komorowski. And so Tomasz Komorowski and Stefan Olaf, I think in 2005. So what Komorowski and Olaf proved is that there is a steady state, and the reason why there is a steady state is because there is an invariant measure with a density with respect to Q. So theorem due to Komorowski and Olaf, under assumptions which I'm not really writing down about the perturbation, then the perturbed dynamics, so with the lambda, has a steady state. So there is the existence of the steady state, nu lambda, but you construct nu lambda as with this density. Actually, nu lambda is absolutely continuous. With respect to Q, so d nu lambda is some density, rho lambda dq. And rho lambda is in L2, but furthermore, you can expand rho lambda as a infinite series, as a power series in lambda, which will be convergent in L2, provided that lambda is small enough. So I should have written it here. You have the existence for small enough lambda, small lambda. So how small depends on the spectral gap. And then rho lambda expands in a power series, in power series in L2 of Q. And from the expansion, you can rather easily deduce Kubo's relation. So this expansion already contains, actually the first order, the linear term in the expansion of rho lambda gives you the derivative, and that leads to a justification of Kubo's relation. So that's one framework in which we can answer all the questions. So still discussing references. There is another reference I want to give with a slightly different point of view, actually with a different point of view, and under different assumptions. And it's a paper by Martin Herr and Andrew Maida. And that one, I think it's from 2010. Yeah, it is. It's called something like a general framework for linear response theory. So all these things around Kubo's relation and so on, they are often called linear response theory, in particular in dynamical systems. By the way, this is a parenthesis, but there is quite a lot of research in dynamical system theory about this kind of thing. there is first-order expansions of SRB states, and you can read this. I mean, Viviane Bahadi gave an ICM talk in Seoul about linear response in dynamical systems. So if you want to know what is the current situation for dynamical systems, you can have a look at this paper. And there are positive, negative results due to Bahadi herself, but also Ruel and other people, Smania, etc. Anyway, Hare and Maeda consider stochastic dynamics. Now, what they did is not really to construct steady states, but they only cared about Kubo's relation. So the result of Hare and Maeda is only about computing the derivative. So you prove that in a certain context, you can compute the derivative of nu lambda at lambda equals 0. And the assumption that Hare and Maeda have is also a spectral gap assumption, but it's not a spectral gap in L2. It's in a different space. So there is some kind of spectral gap assumption. And it is subtle enough to cover cases in which you may have more than one invariant measure for the perturbed dynamics. However, all the invariant measures of the perturbed dynamics under their assumption should have the same derivative at lambda equals to 0. And the spectral gap assumption is rather weak, but still it implies conversions to equilibrium for the unperturbed dynamics at an exponential rate on a certain class of smooth functions. So that implies, as usual, exponential conversions to equilibrium. Okay. Now, one more remark about this paper. It might be of some interest to you to know that the motivation of Hare and Maeda is related to the analysis of climate change. So in the challenges of climate change, there is a problem about guessing, predicting what would be the effect of this or that policy. For instance, if you reduce or increase the emission of blah, 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 what will be the effect on climate? And in the long term. And then the model is, well, the model is actually a dynamical system, but it's a very complicated dynamical system. So it's Navier-Stokes and things like this. But anyway, but the general philosophy is to compute. So what you want to do is, actually you want to know things about nu lambda, which is going to be the new steady state if you modify something from the situation today. So you want to compute nu lambda, but you don't know how to do it. So the only thing you can do is measure things here and now. And therefore, you want to know what to measure today, here, in the present situation, in order to guess what will happen later. And when you do that, what people do is they use Kubo's relation or some version of it in order to make guesses. Now, it's whether this is valid or not. I mean, this is being used. Whether it's justified or not is a discussion between people who actually do climate change. Not everybody agrees. But okay, maybe one motivation for having a general framework where we can justify Kubo's relation is to validate the statistical procedures which are being used in climate change. So, unfortunately, these assumptions, so either the one about the L2 spectral gap, or even the one in Hermida, are not satisfied for diffusions in a random environment. So if we go to diffusions in a random environment, then we have no spectral gap, except in one situation when the environment is periodic. So unless the environment is periodic, now, okay, so if the environment is periodic, then you can apply the conformal result, for instance, but as soon as the environment is random and non-periodic, you lose the spectral gap property. Therefore, we are not in these frameworks, and we have to find another way to approach the problem. So once again, to be a little bit more complete about references, for diffusions in a random environment, for instance, if you take the next simplest case after periodic environment is the case of an environment with finite range of correlation. So typically what you get when Q has a finite range of correlation then we don't have exponential conversions to equilibrium. What we have is a polynomial speed for the conversions to equilibrium. So you have polynomial conversions to equilibrium. And such results are more or less recent results in quantitative homogenization obtained by a whole group of people, including Antoine Gloria, Félix Otto, Jean-Christophe Morat, Scott Armstrong, and others. I don't discuss this at all, although it's natural to think that there should be some connection between the quantitative homogenization results and the Kubo's relation. In any case, it doesn't fit within the framework of Hermida. Okay. Well. So far we don't have anything proved. The only thing we can get from this discussion is that in order to prove Kubo's relation, we will have to find a different strategy. But one thing we can do is make easy guesses. So I erase the thing about computing the mobility, but okay. Now, suppose that we were good enough to find a steady state. So suppose we constructed mu lambda, and now we want to compute the derivative. At lambda equals 0 of mu lambda. So here's a completely unjustified way to compute the derivative. So I evaluate nu lambda at some function f, And I'm going to take the derivative. So I want to take the derivative of this, but this looks a little bit complicated. So we cheat. I don't know how to say we cheat in Japanese. So we cheat, and we say this is, so maybe the first line will be correct, but this is, this new lambda is a limit of some expected value of the additive functional. So the notation was, well, okay, I write it. And then we divide by t. Okay, so if we define the, if we could construct the steady state, this is going to be correct, but now what is less correct, or less justified, is to exchange the order. So as you teach all your students, when you want to take the derivative of a limit, you can freely exchange the order. Sometimes. So I do that, and then we have the same thing. Okay, and then things become much more now things become much easier to do.
In this expression, is both is expectation with respect to an information?
Yeah, I'd agree with you. Under Q. Yes. Thanks. So this notation E was expectation, the unilled one. So this is expectation with respect to E, which is the law of the Brownian motion that is the SE, and Q for the semi-direct product. So, yeah, which is important because we define the steady state as being the limit under Q. It was linked to Q.
I guess you assume that it's also almost surely in E.
In fact, you see what I'm using is not much because I'm just computing the expectation. So actually, the fact what I'm using is just the convergence of the expectation, of the unilled expectation. So when I define the steady state, I stated an almost sure convergence. That would be an almost sure convergence with respect to E and Q. But as a matter of fact, what I'm using here is just the convergence of the mean, of the expectation. So in that respect, it's pretty weak. Anyway. So let us compute this derivative. So we use the Gerstenhoff formula. We have this derivative at lambda equals 0. If I write the Gerstenhoff formula the way it was written last time, is 1 over t, the integral from 0 to t, f of omega of s. Lambda disappeared, and then you have the Gerstenhoff weight, which had this form. So lambda b bar of t minus lambda square over 2, the brackets.
You are dividing the quantity by t twice in the formula.
That's right. So I should erase one of these. Okay, thank you. Okay. So now it's clear what the derivative is. This is the expectation of the 1 over t, integral from 0 to t f of omega s, ds, multiplied by the martingale b bar of t. Okay? And now we are very happy because this is something that we computed last time. And this is a covariance. And last time we proved that indeed that limit exists. and we even gave a name to that limit. It was this correlation operator gamma bar of f. Okay. So that, I mean, the computation is not fully justified. Actually, very far from it. That step is not justified at all. But then the rest is okay, and in particular, the existence of this limit. This was something that we did in the first lecture. Okay? Except that we define this gamma bar on h minus 1. So, if we want to make sense of this computation, we are not going to take the derivative for any f. We should assume that f is in h minus 1. So you see there are two problems. Maybe problem one is justify this step, the second step, but also before doing that, you should define u lambda on h minus 1. And okay, which is not exactly what I was suggesting in the first definition. So there is a problem about what is the right space to work on. By the way, as a side remark, in the framework of Komorowski-Olah with a finite, with positive spectral gap, but also in the framework of Hera and Maida with a spectral gap on a certain space, this h-1 problem is completely bypassed. So if you have a positive spectral gap, then all square integrable functions are in h-1. And then you don't see h-1. You don't see the role of h-1. Okay. So at that point, you might tell me, okay, maybe, so I started at 2:30. Okay, so at that point you might want to take a short break. Okay, so let's make a short break. Seems to be okay. Okay. So I resume from where we were, and now you see if we want to have any hope make sense of this computation, then we have to take h-1 into account. So at that point, you might tell me, okay, then we should define the steady state on h-1, and then we should do this computation on h-1. Now, this is not what I'm going to do, and this is not what I'm going to do, because this is something I don't know how to do. So what happens is that we will indeed make sense of this computation for a certain class of functions or distributions, f, which belong to H-1, but we don't, the results that we proved with Piatnitsky does not cover the whole space H-1, but a subspace of it. So I want to define this, this and these subspaces, and there are two spaces. One is called H-1 infinity. This is the way we called it, and the other one is called H tilde minus 1 infinity. So this notation reflects the fact that the two spaces are subspaces of H-1, but in that case there is one extra condition about some L-infinity bound I will show you in 1 second, and in that case this tilde is because we further impose some regularity on the function. So let me recall from the first lecture, from the definition of H-1, that given an f in H-1, so H-1 is always H-1 of omega, actually it's H-1 of omega and q. So an object in H-1, the distribution in H-1 is of the form f equals div big F, where f, the big F, is an element of L2. So L2 will always be L2 of omega and q to the power d. And the relation between the two f's is just that the integral of g, let's say, f dg dq is scalar product of small f and small g in H-1 in the H-1 H1 duality. So when g is in the Source space H1, and there is a minus. Okay. So H-1 infinity as a set, by definition, is the set of elements f in H-1 for which we can write small f as a divergence of something, but this something, this big F, instead of being in L2, we will assume that it's in L infinity. I'm sorry, but I think that my notation I have the 2 upstairs. So this is a set of small f such that there exists a big F, but now in L infinity to the power d, such that small f is the divergence of big F. Now you can put a norm on that space by looking at the L infinity norm of big F, and you minimize. So the H-1 infinity norm of F will just meet the minimum of the L infinity norm of big F, where big F is such that small f is a divergence of big F. So this defines a subspace in H-1. A typical example of an element in H-1 infinity is a drift term in the SDE. So this B, which is 1/2 of the divergence of A. Let's say in a direction E. Okay. And then, well, it's written in this equation that B is a divergence of A, and A, we assume that A is bounded. So this is indeed in H-1 infinity. Another remark is that the big F, such that the divergence of F, big F equals small f, is far from being unique. Okay, so in general, at least, F such that the divergence of F equals small f is usually not unique. hence the minimum. The set of f's that solve this equation is a linear space. And that's a first space, and then there is a second one, the one with the tilde. And the one with the tilde is same thing, except that we require some smoothness. So now it will be this set of f's which are in h-1, actually in h-1 infinity, for which you can find a big F, which is bounded but in fact continuous. Such that's more or less equals the divergence of big F. So h tilde minus 1 infinity will be a subspace of h-1 infinity, a closed subspace. In h-1 infinity, it is generated by, for diffusions in a random environment, it's generated by functions, big F's, which are local functions. Okay? So I don't have a very convincing motivation for introducing these spaces for the moment, but actually the motivation comes from the results that we are able to prove and from the proofs themselves. So that leads to a second definition of a steady state. Let's say steady state. Definition 2. So in definition 1, the steady state was an invariance measure, but in definition 2, it's going to be a linear functional on h-1, but in fact not h-1, but h-1 infinity or h-1 tilde infinity. So a continuous linear functional on h tilde minus 1 infinity, u lambda, is what we call steady state. If we have a law of large numbers, so 1 over t times integral from 0 to t f of omega lambda of s ds converges to u lambda of f. Now, this convergence we want it for f in h-1 infinity tilde in a certain sense. Now, in what sense this should converge, I think it's not very, very important. But just for the sake of having a definition, let us say that this is holds in L1 with respect to P and almost surely with respect to Q. But actually, as the previous computation showed, what we really care about is taking the expectation. So this is more than sufficient, but you could change that if you want. The only important fact is that we restrict to functions or distributions f in h tilde minus 1 infinity. H minus 1 infinity tilde. Okay. So, with a little bit of imagination, you can define similar spaces in an abstract framework, but I want to consider my diffusions in a random environment. So here I'm considering diffusions in a random environment as last time. And in particular, I'm assuming the three assumptions A1 into A3, which I recall were about the environment is stationary and ergodic. The coefficients, the diffusion coefficient A, which is over there, is smooth and uniformly elliptic. And then we have a theorem. So recall that what we would like to do is take the derivative of the steady state. So first we should prove that it exists. But knowing that it exists, we would like to take the derivative. Now this theorem is not going to do that, but it's encouraging. The theorem is about the Lipschitz continuity of the steady states. And the steady state, the way I just defined it, so the steady state in the sense of definition 2. Okay? So here's the statement. So assume that there is a steady state u lambda for small enough lambda, say lambda between 0 and 1. And here the steady state is in the sense of definition 2. Then it will be Lipschitz continuous. That is, then you will get the following thing. So I should have started the statement by saying that there exists a certain constant C1 with a property that if we have a steady state, then we have an inequality of the form u lambda of f is less than C1 times lambda times the norm of f in h minus 1 infinity. And this for all functions or distributions f belonging to h tilde minus 1 infinity. Well, yeah. Okay. So this is not quite what we want, because what we would like to do is to compute the derivative. But at least here we see that when lambda goes to 0, then the steady state nu lambda is approaching Q. So just, I mean, maybe I should emphasize that the following remark, that if you have an f which is in h minus 1, it's automatically centered with respect to Q. So if f is in h minus 1, then Q of f is 0. So this statement about, in particular, nu lambda of f tends to 0, you should understand it as a way to say that nu lambda of f converges to Q of f. So nu lambda is converging to Q. Now, okay, so I still have a little bit of time, so I'm going to give a proof of that theorem. Okay, so I make the proof. The proof is actually not very difficult, but I will also introduce some objects that we will use later on. So, to start the proof, we start with an f, small f, which is in h minus 1 tilde infinity. Well, at that point, the tilde is not very important. Never mind. And we know then there is a big F in L infinity, such that small f is the divergence of the big F. And I will assume, without loss of generality, that the L infinity norm of F is bounded by some constant 2. And next. So we will go to RD. So I will use the notation F omega of X. This is the space realization of F. So this will be F of X dot omega. And similarly, big F omega of X is big F of X dot omega. So we are, okay, so with this notation, the fact that small f is in the divergence of big F, this is a divergence in omega space. But this translates into the relation that F omega is a divergence of big F omega in RD for the standard divergence operator in RD. So we have this diffusion, say, starting at point X, which we define as a solution of a certain SDE. We want to take into account an additive functional like over there. So the trick to do that is to look at the D plus one-dimensional process that you obtain by looking at the diffusion itself and adding something, last component, which includes the additive functional we want to look at. So f of omega lambda of s ds. And I want the process to be non-degenerate, so I will artificially add an extra diffusing Brownian motion. So let us look at this R d plus one-dimensional process, which we denote by z. So it depends on lambda omega. Starts from a certain point, z at time t. So the notation is as follows. So this process is R d plus one valued. And I'm using the notation for, so a typical point z in R d plus one, I will write it as a couple x, y, where x is in Rd, y is in R. And this W1, so this W1 is independent one-dimensional Brownian motion. A statement of the theorem will follow from some a priori bounds on this process, Z. So let us write the generator of the process Z lambda omega. So this is a certain operator, M lambda omega. And what is it? So in the x coordinate, it is like the generator of x. So I write it, okay, I write it, 1/2 div A omega grad. So this is the part without the drift. And this is in x. So these operators act on x. And you have the drift part, so plus lambda v1 dot A the gradient in x. And then we have the part that depends on y, so there is a diffusion part which is constant, so 1/2 second derivative in y, plus something which comes from the drift, which is f times first order derivative in y. So this is the part we should be a little bit careful about. So I want to rewrite that operator in a divergence form. And in particular, I want to rewrite the last term in divergence form. So let me just keep the beginning. And rewrite the last term. So my claim is that the last term, I want to rewrite it in terms of the big F. So, so this guy is a divergence in X of big F. So I use this. So I'll get the divergence in X of big F times the derivative in y. But if you do that, you make a mistake. So you will have the divergence of f times the derivative. This is what we want. But then we will have f times the divergence and the derivative in y. So I have to subtract something, which is the derivative in y of f times the gradient in x. Okay? And this is correct because actually big F does not depend on y. So when you compute this last term, what you get is f times the derivative in y of the gradient in x. So because f omega does not depend on y. Okay. So this is the generator of Z written in divergence form with coefficients which are all bounded, because A omega is bounded because we assumed it is. Here it's also A omega and it's also bounded. This is just a constant coefficient. And here, big F omega, which appears here and there, we are also assuming it's bounded. So we can, I mean, we have a bunch of estimates on solutions of operators in divergence form with bounded coefficients. Now, to write things properly, the first thing to do is we change the scale. Now we change the scale and introduce new variables, which are rescale variables, which will have a tilde on them. So I rescale space by a factor lambda. That is, I define z tilde to be lambda z, and I rescale time. So new time is t tilde by a factor lambda square. So we are doing diffusive rescaling, and then the rescaled process, let's say with the tilde, so z tilde lambda omega x times t. By definition, this is lambda times z lambda omega at time t over lambda square, and the starting point is then x over lambda, so that they both start from the point x. Actually, I should not be using an x. I should use z tilde, because x for the thing in. Okay, sorry. Okay. So I use Z as a starting point because I am in RD plus 1, and Z tilde starting from small Z tilde is the same as Z starting from Z, with time rescaling and a space rescaling. And we have to look at the effect of this rescaling on the operator. So the generator of this guy is a certain operator, M tilde lambda omega. Now what happens is that when you make a change of the space variable, each time you have a derivative, you have a lambda coming out in the formula. But on the other hand, because we rescale time, we multiply everything by lambda minus 2. So the first term is not going to change. I mean, it's going to change, but you multiply by lambda because of this derivative, then you multiply by lambda because of this derivative, and then you multiply by lambda minus 2. So these things cancel, and you get 1/2 divergence in X. Now, of course, we should rescale A omega, and then the gradient. Okay? Then, second term, you only have one derivative, so you multiply by lambda, but there is already a lambda, and then you multiply by lambda minus 2, so these terms cancel, and you get E1 dot A omega at point dot over lambda, and then the gradient in X, okay, etc. So the second term is the second derivative, so no change. Anyway, the coefficient was constant. And then this term has two derivatives, so the lambdas disappear, but we rescale F omega. E1. And okay, everything is wrong, but I'm going to correct. And then the last term is also a second derivative, so we get omega that we rescale. Check. And then we get the gradient next. So, okay, so everything is like this, except that it's all in tilde variables. So you should put tildes everywhere. Okay. Anyway. So this is a family of operators in divergence form. We have uniform bounds on all the coefficients, which are uniform with respect to space and with respect to lambda. So we have bounds on the solutions, say Aronson bounds, which are uniform. So they are uniform with respect to lambda, to omega, provided you work on a. So they are also uniform with respect to space, to Z tilde, and I'm going to use Aronson bounds for a finite time interval. So let's say that we consider the case where time, T tilde, is less than 1. Now, okay. So then there are 100 different ways to conclude, but for instance, you can do the following thing. There exists a delta 0, which depends on, well, in particular, it does not depend on omega, does not depend on lambda, such that if you look at that process over there, Z tilde, then by time 1, you stay in a ball of radius 1. So it's the probability. Now, it's a single p. So the probability that Z tilde lambda omega at point X stays in the ball of radius 1 is bounded from below by delta 0. And delta 0 is positive. So it stays in this ball until time 1. Okay. And the past starting point is C. Thank you. And sorry, well, the starting point is the starting point can be for this estimate 0, for instance. I think 0 is enough.
But you said that there is a zero.
Sorry?
Uniformly with respect to lambda, omega, delta, it is.
Uniformly.
With respect to lambda,
Yes.
the tilde, tilde you have this one, but there is no z tilde.
No, there is no z tilde, but it doesn't mind, I think, because it's, in fact, uniformly with respect to z tilde or uniformly with respect to omega. So that's why I think it's enough to start from 0. Okay. Then once you have something like that, you play a little bit with the Markov property, and from that you would deduce that for any p there is a certain constant Cp, which does not depend on omega, so for all omega, and also for all times t which are greater than 1, then I mean this implies that the process z tilde it's not faster than ballistic. So the kind of bound you get for the moment is, if you look at, so I'm going to write in terms of z, but in terms of z tilde, I'm looking at, for instance, the maximal value of z tilde up to a certain time t. So that corresponds to time t, big T over lambda square for z. B lambda omega started at 0, taken at time s, to the power p. So here what I wrote is the sup of z tilde on a finite time interval, and I claim that this is bounded by some constant times time to the power p. And going from the first claim to the second one, it's a very elementary exercise using the Markov property. And so you see that contains, in particular, the conclusion of the theorem, because so you can take the case p equals 1, and what we were interested in is the steady state. So we look at lambda, well, the inverse of time, which is lambda square over t, times the expectation of the, just in this norm, there is in particular the last component of z, which contains the additive function. So the last component of z, when started at 0, this is the integral from 0 to t, f of omega lambda of s, ds, plus this Brownian motion. Now, on the scale we are looking at, the Brownian motion doesn't contribute. So it follows from this line that you have a similar thing if you look, so maybe I don't take the max anymore, if you only look at the additive functional. So I take the integral from 0 to t over lambda square, f of omega lambda s. Yes. I can put absolute values, actually wherever I want, but if I want to go to the statement of the theorem, I put them outside, and then this is less than C1 t, so this is for t equals 1, and what we really want to do is to take the limit when big T tends to infinity, so we would like to multiply by the inverse of time, so I'm multiplying by lambda over t, and then I get a C1 lambda. The upper bound. And then we can let t tend to infinity. So when t approaches infinity, this is going to tend to the steady state. I'm assuming that the steady state exists. So I will get as a limit u lambda of f bounded by something linear in lambda. Okay. So as you can see, we can do better. We can do LP bounds, and we can put the max inside, etc. And so that proof is not very difficult, and it's also, I mean, these estimates are quite robust. Okay. Is this okay? Yeah. Okay. So, just since I see I still have a couple of minutes, I'll do two things. So, first, what comes next? So, the remaining part of the program will be to justify Kubo's relation. But before we do that, we will have to check the existence of the steady state nu lambda, either in definition 1 or in definition 2. The statement of the previous theorem was in the case of a quite arbitrary, uniformly elliptic random environment. But the existence of nu lambda, and in particular the justification of Kubo's relation, this we only know how to do it under assumption 4, A4, which was about the finite range of correlation. So in the next lectures, I will describe the proofs of the Kubo relation for random environments with a finite range of correlation. And then the last point I want to make today is about the terminology. So, and since I lost my notes, okay, because, okay, so in the papers we wrote, in particular in the paper we wrote with Andrei Pertinsky and Nina Gantwert and myself, we said that we were proving the Einstein relation. And what we actually proved is that the limit of x lambda omega of t divided by t exists when time tends to infinity, so there is a law of large numbers. It gives an L of lambda, but this was already known. And what we really proved is that 1 over lambda L of lambda tends to sigma E1 when lambda tends to 0. And we call that Einstein relation. Now, I think this is questionable. I mean, the calling that the Einstein relation is a little bit questionable. But this is, okay, this is what probabilists call this relation, so we could not really change the name. Now, it should be called Kubo relation or Green Kubo relation or something like this. So there is a lot of ambiguity, but if you read Einstein himself, then Einstein's computation, Einstein's relation, I think it is more about what it means to have a constant force. So I told you what it means to have a constant force is you take the generator and then you add this constant term. So the way we modified the generator to include the constant force is we write something like that, right? This is the generator of X. And I think that the Einstein relation is the relation, from what I understand, between the diffusive part, which is here, and the drift part, which is here. So you see, the two things are related. And so this form of equation should be called mesoscopic Einstein relation. So if you are a physicist and you want to understand what it is to impose the constant force, you have to do some reasoning to justify the form of the modified generator. And Einstein himself does something like that, and it leads him to this kind of local relation between the drift term and the diffusive term. And at the level at which this equation describes the dynamics is mesoscopic one. And in the previous lecture, we showed that in the scaling lambda square t equals 1 or alpha, then the limit of the corresponding diffusion is a Brownian motion plus drift. So the limit had a certain covariance matrix. Okay, now I'm not writing the generator, but I'm writing the process. Never mind. So this is a Brownian motion with this covariance matrix. And we computed the drift term, which turned out to be square root of alpha times sigma E1. So this drift term times time. You see? So in a sense, and then the relation between this term and this term is just preserved in this limit. Right? So what the argument of Leibowitz and Rost proves is that the Einstein relation survives in this scaling limit. And actually, the Leibowitz and Rost argument proves that this is the case under quite general assumptions. This is a very soft argument. So in the beginning of their paper, Leibowitz and Rost argue about that. And I just believe they are right. That is, indeed, this, I mean, if in the Einstein's papers, you do see things like this. Okay, now what now we call Einstein relation is on a different scaling. It's in the scaling where t tends to infinity, and then lambda tends to 0. And in that scaling, what we get is not a diffusion process. It's just the speed. So now what is known as Einstein relation is the fact that 1 over lambda L of lambda converges to sigma E1, which is some kind of infinite time, or it would be better to say alpha tending to infinity relation. But okay. So, I mean, this is the way it is now. this relation is called the Einstein relation, but it's difficult, for instance, for students, but even for us, if you call this an Einstein relation and then you go to the papers in Einstein's papers, for instance, or you go to the physics literature in general and look what, or you go to Wikipedia, wherever you want, and you look for Einstein relations, and you will not really find this. You will find this if you look for keywords like Kubo relation, Green-Kubo relations, or linear response, or fluctuation-dissipation theorems. Okay, this is something I haven't mentioned, but
so who started to
one
call
name.
this as the Einstein relation?
You mean among mathematicians, probabilists?
Yeah.
Who is guilty? That's your question. I don't know. I don't know. Yeah, but I don't think it was really Einstein. Okay. So thank you, and maybe continuation is next Friday. Okay. Yeah. Questions?
In the theorem, you use this Aron function bound and this kind of tightness estimate. But the estimate itself looks kind of weaker than, may hold without outside the situation that nice are also more. I don't know.
Yeah.
In this situation, of course, you can use it. So am I right that this estimate may hold by the framework?
In more general context, you mean?
Yeah.
So I don't know. It depends what kind of context you have in mind. Because you might think about relaxing the assumptions on the diffusion coefficient.
Yeah, for instance.
And then probably you're right. But one question is, here it works because, so we assume that small f is in h1 infinity, h minus 1 infinity. That's important. And then there was a question about f being the divergence of something, and this something being in L.2. And then I'm not... Okay, which is also a question you can ask, and I do not know whether it's true or not, even for a large Q. But the assumptions about the uniformitticity of the coefficients, yes, in fact, this is a statement. You can relax. You can very much relax them. Any other question?
Comments? Thank you very much.
My pleasure.